So we have just looked at several biasing configurations, and we concluded that the emitter biasing was one of the most stable configurations. And in the form that was most stable was when we had our base supply being lower than VCC and our emitter voltage being around 1 volt. Now we're going to look at the practical implementation of that biasing configuration. And the reason why we cannot just do it the way we originally designed it is, well, typically in a circuit, we don't have as many voltages as we would like. We typically have the supplies that are available, typically the positive supply, VCC, maybe a negative supply, and sometimes you may have a third one, but you certainly cannot just set the base voltage or the base supply voltage to whatever you would like. You typically will need to use one of the available supplies and then bring it down to whatever value you need. That's a more practical implementation. And so one way of doing that is by using a voltage divider network. And that's why this configuration is called the voltage divider bias. So let's do voltage divider. And again, just to review, we had our biasing configuration was looking like this. We had the transistor connected to VCC via a collector resistor. We had an emitter resistor RE, which provided the emitter biasing. And then we had our base resistor connected to the base supply VB. And again, we wanted to set VBB lower than VCC. A practical implementation of this could be by using the same supply VCC and using a voltage divider to implement VBB. This is R1 and R2. Because of the configuration with 4 resistors, this is often also referred to as the 4-resistor biasing network. It's one implementation of emitter biasing. We're going to keep our VCC, as in previous examples, set to 10 volts. And we're going to still try to set our Q point to IC of 1 milliamp. So how do we go about designing this voltage divider biasing network? Well, the first thing is we're going to set the emitter voltage to 1 volt for stability purposes. Remember, this is collector, base, and emitter. So step number 1 is set VE to about 1 volt. For stability, we saw that that made it more stable for from the perspective of beta, for beta variations. We will see later on how this also makes it more stable with respect to temperature. Now, why 1 volt? Why not, 2 volts, 3 volts, 5 volts? Well, at some point, if you keep increasing the voltage across the emitter resistor, you're going to lose signal swing, assuming that you take the output at the collector terminal, the output of your circuit, which will be the case in several of our amplifiers. And so 1 volt just seems like a good trade-off between, keeping still a significant portion of your signal swing, your output signal swing, and gaining that stability. After that, if you keep increasing the amount of stability that you gain, does not justify the loss in signal swing. So we're going to use 1 volt as a rule of thumb. There's going to be many rules of thumb that we use as designers, which it's not like it is the absolute right value. There's nothing that says it couldn't be 1.2 volts, 1.5 volts. The circuit will still work if you make it 2 or 3 volts. But again, it's just, we're considering a value that's going to give us a good trade-off between different parameters. In order to do that, we are going to calculate the required value of the emitter resistance. RE is going to be by voltage, by Ohm's law, equal to the voltage divided by the current. And we just will continue to use the approximation of IE as being close to IC. This is going to be 1 volt divided by 1 milliamp or 1 kilo ohm. So by setting RE to 1 kilo ohm, we're setting the emitter voltage to 1 volt. Step number 2, we want to set our base voltage to the correct value. Obviously, we are going to want to turn on our transistor, and so we need 0.7 volts across the VBE junction. But the emitter voltage is already set to 1 volt, so 1 volt plus the 0.7 required to turn on the junction give us a base voltage VB of 1.7. So the next thing we're going to do is try to set VB to 1.7 volts. Now, since we have a voltage divider network, the value of VB, the value of the voltage there on the voltage divider, at the output of the voltage divider, is going to be proportional to the ratio of those two resistors, R1 and R2. I'm going to redraw the voltage divider so this becomes more clear, perhaps. This is our VCC voltage, and we are dividing it between R1 and R2. V1, V2, where we can write, V2 is equal to R2 divided by R1 plus R2 times VCC. I notice that R2 is, by the way, the base voltage. I'm going to just label it here. So I'll say base voltage equals V2 and equals that from the voltage divider equation. Or we can write it as V2 over V1 is equal to the ratio of R2 over R1. That's another possibility. Now this is true for the ideal voltage divider, and by ideal I just mean it's connected, the output is connected to an open circuit. In most practical applications, we're going to have some kind of load connected to our voltage divider network. And so that means that in this equation, we're not really considering the value of R2, but rather the parallel combination of R2 and RL, what we could call R2 prime, right? So we could say right here, R2 prime is equal to R2 in parallel with RL, right? And so in our equations, this will really be R2 prime, that's R2 prime, and this will be R2 prime. Now we know that when we have two resistors connected in parallel, the parallel combination is approximately equal to the smallest of those resistors when the condition is met that one of those resistors is much smaller than the other one. And so we can say R2 prime is approximately equal to R2 if R2 is much smaller than RL. And so in our voltage divider biasing network, we're going to want to meet that condition. We're going to want to have R2 being much smaller than RL. But what is RL in our case? Well, RL is going to be the resistance looking into the base of the transistor. Now, if you recall, for resistance calculations, the transistor sort of acts as a lens. So let's imagine I have a transistor, and this is my base resistor or overall resistance connected to the base, and this is the overall resistance connected to my emitter. When I am looking from my base towards the emitter, right, I'm looking into the base of the transistor. This base of the transistor acts as a lens that amplifies whatever resistance is connected to the emitter by a factor of beta. So when I'm looking from here, I say RE looking from the base is equal to beta times RE. Likewise, when I'm looking from my emitter terminal at the resistance that's connected to the base, I still have to look through the same lens, but in this case I'm going to get the opposite effect. I'm going to see the resistance that's connected at the base divided by or reduced by a factor of beta times smaller. And so my resistance at the base is looking from the emitter is going to be equal to RB divided by beta. And so we can apply that principle, that approximation, into this example. And when we look at RL, or the resistance looking into the emitter, is going to be equal to beta times that emitter resistor. And so in order to maintain our voltage divider stable, we want our R2 resistor to be much smaller than that resistance looking into the emitter. So we want, choose R2 as being much smaller than beta times RE to avoid loading. Of voltage divider network. Now, how much is much smaller? Well, we're going to use a rule of thumb, and by our rule of thumb, we're going to try to make it at least 10 times smaller. So R2 will be less than or equal to 1/10 of beta times RE. 1 order of magnitude. From there, any lower that we go, it's just better. It just will make our voltage divider more stable. We also don't want to go too low, because if we have very small resistors in our voltage divider network, well, then for the same voltage levels, smaller resistors, we will be having more current through them, which means we'll be consuming more power. So we don't want to make them too small in order not to increase our power dissipation, but we don't want to make them too large in order not to have loading effects. That's another one of those trade-offs. But if we meet that rule of thumb, then we will have that R1 over R2 will be approximately equal to VCC, which is 10 minus the base voltage, which is 1.7, or 8.3 divided by 1.7. And so we're going to select R2. Again, there are multiple values of R1 and R2 that will meet this. We just need to choose an R2 that is less than 1/10 of beta times RE, and that is 1/10 of 100 times 1K, which comes out to be 10K. So we want R2 to be less than 10K ohms. Let's choose 8. And that will make our R1 be equal to 39 kilo ohms by applying that ratio. So we've designed our voltage divider network. This is 39 kilo ohms. This is 8 kilo ohms. And the last thing is to determine the value of RC. And we're going to determine RC so that we center the value of VC. And the reason why we want to center it, as we mentioned previously, is a lot of the times, for a lot of the circuits, we're going to have our output taken out of the collector of the transistor, and we typically want to have a large amount of signal swing at that point. So we want to be, far from the supply, far from both supplies, really, so that, our signal can swing both in the positive and negative direction. So we choose RC to center VC at 5 volts. And RC is going to be equal to VCC minus VC divided by 1 milliamp, or IC. So 10 minus 5 divided by 1 milli is equal to 5 kilo ohms. And that's our last value. So we've designed now our voltage divider biasing network for an IC of 1 milliamp, and our VCE, we don't know what it is just yet, we can calculate it. So key point will be an IC of 1 milliamp, and VCE equal to VCC minus ICRC minus VE. So it will be the total voltage minus the voltage drop across RC minus the voltage drop across RE. That will be what's left for VCE. In this case, it's equal to 10 minus ICRC is 1 milliamp times 5 kilo ohms or 5 volts. The NVE is 1 volt by design, and so this will be a VCE of 4 volts. So that's our Q point. If we simulate the circuit, it'll probably not be exact, but we should expect that because it is an emitter biasing configuration with the conditions that we had already seen improve the stability, we should expect that it will be stable to beta variations. Thank you.